Hey, grade 12. So today we're going to look at how stoichiometry affects the rates of the reaction. In other words, how all the reactants and products are related in terms of their rate. The stoichiometry of a reaction will be, we can actually use that to find the rate of decomposition of our reactants or the production of our products. In other words, if we know the rate of one species in a reaction, we can find the rates of the others because they should be proportionate. Here's an example. So if we look at this reaction, two NO2s makes two NOs and O2, you should get a graph that looks something like this. Now, it can be seen from the graph that there's kind of a bit of a pattern here. So the first pattern I want to look at is the changes or the different curves for NO and NO2. So we're going to look at the red curve, reddish-orange curve, and the green curve. And if you look at those two curves, they're the same curve. They're just one is flipped over. So if you look, the ratio is a 2-to-2 ratio. So the rate of one is going to be the same as the rate of the other because they're a 1-to-1 ratio. It's just one is increasing, one is decreasing. But if we look at if we compare the curves, the red curve and the blue curve, now what you should see is that the blue curve is exactly half that of the red curve. And the reason for it, well, oxygen is being made at a 1-to-2 ratio. It's being made half as fast as NO. So because they're related through stoichiometry, we can actually, if we know one rate, we can calculate all rates rather than doing them one at a time. So what the graph is showing us here is that the rate of decomposition of NO2 is equal to the production of NO because their ratio is 1-to-1 or 2-to-2. So every time one is used, one is made. It's almost like at a automobile manufacturing facility where you're using, every time you use an engine, you're making a car. So the rate of engines disappearing from the shelf should equal the rate of cars appearing on the lot. The rate of production of oxygen should be half of that because it's a 2-to-1 ratio. So we can actually set up something called an equality or mathematical expression to show the relationships of these rates and kind of show the stoichiometry of the reaction. So if we set everything up to be equal to the rate of oxygen, we would get an equality that kind of looks like this. So I'm going to start with oxygen. So rate is going to equal the change in concentration of oxygen over the change in time. Now to make, let's take nitrogen oxide. To make that rate the same as the rate of oxygen, we would have to make it half as much because it's a 2-to-1 ratio. So I'm going to say, well, that's going to be equal to half the rate of NO over change in time. And it would be the same for this one because it should also be half. So it would be equal to half the rate of NO2 over time. Sorry, change in NO2. But the problem is because this one is decreasing, these ones that are increasing, because the value would end up being negative, we'll make it positive by multiplying it by a negative. So that's something called an equality. We're showing how they're all related to each other. So here's another one. We can do just a simple reaction. A and B makes D. If we want to set this reaction up as an equality, just like I showed you above, we're going to pick one of the reactants or products, and we're going to make everything else equal to it. So I'm just going to do A because I find that's the easiest one. So the rate for A is the change in concentration of A over the change in time. Well, to make B equal to A, it's a 3-to-1 ratio. So B is going to be changing 3 times as fast as A. So to make it the same as A, I'm going to have to times it by a third. So the change in B over time. And then to make D the same as A, well, D will be increasing twice as fast as A is decreasing. So to make it the same as A, first of all, because D is increasing and A is decreasing, I'm going to make it the opposite sign. And it's going to be half. I've got to make it half as much, the change in D over the change in time. So that's how we could set up our ratios just to show that. When we're doing stoichiometry with this, though, we're going to set them up just the way we've been doing all along, but it's good to kind of get these mathematical relationships out of the way as well. So here's a reaction, the same reaction we were working with. If I'm given one rate, we can find the rate of anything else. So if we look at the question, it gives me the rate of NO2 at 0.6 mole per liter per minute. So I'm going to write that down, 0.6. I'm going to write it as moles per liter times minutes. And we want to find the rate of oxygen. This is the rate of NO2. So I want to go from NO2 to O2. So I can see that O2 and NO2, there's a ratio between them. 1 mole of O2 is made every time I use 2 moles of NO2. So I take my 0.6 times it by half, and that rate is going to be 0.3 moles per liter times minutes, not seconds. And that's for oxygen. If we have a rate of NO2 is 0.5, so 0.5 moles per liter, in this case is moles per liter seconds, this is of NO2, we want to find both products. So we're going to go, let's do NO first. So we're going to times by 2 moles of NO for 2 moles of NO2. So it's going to be the same, 0.5 moles per liter times seconds for NO. But if I want to get to oxygen, it's going to be 1 mole of oxygen for every 2 moles of NO2. So it's going to be half again, so 0.25 moles per liter times seconds of oxygen. Now here's one for you to try. Give it a shot. Maybe pause the video, give it a shot, and then hit play again, and you can check your answer. So if we're given the rate of A is 0.6 moles per liter times seconds, and we want to find C and B. So let's start with C. So we're going to get rid of, this is for A, we're going to get rid of A, so the moles of A on the bottom, moles of C on the top. It's a 3 to 2 ratio. So 0.6 times 3 divided by 2 should give us 0.9, and that will be moles per liter times seconds of C. And then I'm going to do the same thing, but with a different ratio for B. It's 1 mole of B for every 2 moles of A. So that's going to be 0.3 moles per liter times seconds of B. And that's what we can do. We can find, if you're given one rate, we can find all of the rates.